Okay, everybody, I think we're going to get rolling here. I want to welcome you here today. My name is Susie Taylor. I work at Montana State University, and I'm with Extended University. I want to say thanks to everybody who's here with us live online, as well as those of you who will be watching the presentation later through the archives. The course that we're offering is called Montana's Changing Climate, and we'll be offering a presentation every morning, Friday morning at 11. All the talks are presented by researchers with the Institute on Ecosystems, and they're all working on a project called the Montana Climate Assessment. The Montana Institute on Ecosystems is a statewide interdisciplinary institute originally launched with support from Montana NSF EPSCoR, which is a program of the National Science Foundation. The goal of the IOE is to build a community of researchers and stakeholders who come together for science and collaboration. The IOE has offices here at MSU in Bozeman and at the University of Montana in Missoula. You can learn more about IOE at montanaioe.org. A little bit about the Montana Climate Assessment. It's the IOE's largest project. It's something we're very proud of. Many states have completed a project like this, a climate assessment of their area. There's even one for the United States as a whole, but Montana has never done a comprehensive report like this, so we're very excited. The report should be released later this summer or early fall. For right now, we're focusing on 3 major areas. Those are agriculture, water, and forests, and we came to those through some listening sessions that we did all around the state. There will be an opportunity to tackle other topics as well, and we will be looking for some stakeholder input on what those topics should be. Our speaker today is Kelsey Jainso. He's head of the Montana Climate Office based in Missoula. He's also a professor of hydrology at the University of Montana. He's the author of the main climate chapter of the Montana Climate Assessment. Our future speakers on following Fridays are Wyatt Cross, who's at MSU and also with the Montana Water Center, Ashley Ballantyne from the University of Montana, and Bruce Maxwell from MSU. So just one last time, I wanted to mention the question chat boxes that are at the bottom of your screen. There are 2. One is on the bottom right, and that's for technical issues. If you're having trouble with your audio or anything else, you can type that there and we'll try to help you out. The other question pod is for general questions that you can type for our presenter or about the IOE or the Montana Climate Assessment in general. We'll actually compile all those questions. You can type them in at any time, but we'll save all of those for the end of the presentation today. There's a poll that will stay open on the bottom right of your screen. You can do that at any time. And then we will be archiving this presentation along with associated links and other information. The link to that is in the top right of your screen. It's called Webinar Archives. And we will also send that to everybody who's registered in an email. So you have that link easy at hand. And just so you know, for those of you who are planning to join in every Friday, we'll be using this exact same link, the one that you used to log on today. So hang on to that. We'll send you a couple of reminders, but just so you know, you can bookmark or just hang on to that link. So thanks again for being here today. I'm going to turn it over to Kelsey. Thank you.
Well, thanks a lot, Susie. Hello, everyone, and I'm really excited to be here. Give me a minute, and I'm going to switch over very quickly, turn off my webcam here and start the presentation. And everyone should be able to see my first slide, I'm hoping. Okay, we'll try this again. Okay, so I think that's working. So good morning, everybody. Again, I'm really excited to be here today. As Susie said, and that was a great introduction, my name's Kelsey Jainso. I'm the Montana State climatologist. I'm also an assistant professor of watershed hydrology here at the University of Montana. Today I'm going to talk about Montana's climate, past, present, and future. And really this talk is again a part of the Montana Climate Assessment, an ongoing effort across the university system and led by the Institute on Ecosystems, many faculty across the university system, in an effort to understand kind of where we've been in terms of our previous climate, where we are today, and where we're moving towards in the future. And then we'll talk about some of the impacts in terms of potential impacts in terms of agriculture, forests, and our water resources. Hey, before I jump into the details of my talk today, I just want to take a second and recognize the Montana Climate Office staff. All of the people here have contributed to the data and analyses that I'm going to talk about today. And I've just shown some images of our staff. Mike Sweet is our information services provider. He runs the day-to-day in terms of our website and provision of information. Nick Silverman, I really have to recognize Nick. Nick did the most of the analysis and figures and of the work that I'm going to discuss today. Kevin Hyde is our Mesonet coordinator. The Mesonet is a beginning weather network and soil moisture monitoring network that we're working with Ag Extension and the MSU Ag Research Centers to install across the state. It's transmitting variables like weather data as well as soil moisture information in cropping environments, and it's doing that every 30 minutes. So Kevin spends a lot of time driving around the state and installing these stations. Okay, just in general, the Montana Climate Office's goal is to provide high quality, timely, and relevant climate information and services to Montanans. As part of this effort, we were really excited to join the Montana Water Center campuses of the university system and the Madison River Group, really in a joint effort to develop the first Montana climate assessment. I should highlight that this whole large effort is being led by Kathy Whitlock at the Institute of Ecosystems. Okay, so I've shown kind of the general framework of the climate assessment here. The first step was to develop climate analyses, both historical and assess current climate, but also understand how we're moving forward into the future. The sector leads in terms of the impacts of climate change and our discussion of that include the really relevant sectors in Montana. These are agriculture, led by Bruce Maxwell at Montana State Land Resources and Environmental Sciences, water resources by Wyatt Cross, director of the Water Center and professor of ecology at MSU, and finally forestry, led by Ashley Ballantyne here at the University of Montana. Again, we're all wrangled by Kathy Whitlock at the Institute of Ecosystems. So generally, the Montana Climate Assessment is an effort to synthesize, evaluate, and share credible scientific information about climate change in Montana. And the goal is to do this with citizens of the state. Our group's current focus is on the three of the most Montana's important sectors, again, agriculture, forests, and water. The motivation really behind the climate assessment arose from citizens and organizations across the state who've really expressed interest in receiving timely information about climate change, and including information about our historical variability, our current trends, and the potential projections of future impacts. Okay, this has been an ongoing process. We've been working on the climate assessment for some time now. We began with a series of listening sessions across the different sectors, so ag, climate, and water, to determine how groups such as agencies, landowners, tribes, others, private citizens considered climate in their day-to-day activities. We received a really vast array of topics, that Montanans consider in terms of their day-to-day activities, their decisions, their concerns. After this, we spent roughly January from November 2016 working on analyses and writing up our results across the different sectors. Finally, we've reached the communication phase, and I'm excited to kick it off here today by presenting a brief version of our climate section findings. Again, these will be brief. The final climate analysis report will be released, as Susie said. We were thinking spring, but into the summer now, and this will provide a lot more detail.
Hey, Kelsey.
So let's jump right in.
Kelsey, this is Susie. I'm going to interrupt. Sorry. We're
Sure.
kind of seeing your entire screen with the notes in the next slide. I know that's kind of a Mac presenter thing, but you might want to take a second real quick and just see if you can swap that.
Thanks, Susie.
Yeah, no problem. Sorry to interrupt.
No, thank you. How is that? No?
Nope, we still see, I think it's that Mac presenter thing.
There we go.
Yes, excellent.
Okay, thank you. Okay, so let's jump right in. Let's ask the question, what is climate and why does it matter? Generally, climate is a measurement of the mean, the variability of global and regional atmospheric processes, and it varies over different timescales. They can range from decades to thousands of years. The kind of the standard definition that's incorporated by the World Meteorological Organization is about 30 years. If I was to put it more simply, climate is usually defined as the average weather in a given place. It includes patterns of temperature, precipitation, both in the phase of rain and snow, very relevant here in Montana, humidity, wind, and seasons. And these climate patterns really play a fundamental role in shaping our natural ecosystems, as well as our economies through differences in agriculture and productivity, as well as water and water availability, as well as fundamentally just our culture here in Montana. Okay, so when we consider climate, there are a ton of variables. So more than 50 in total that's considered by the World Meteorological Organization. However, in general, the main climate variables include temperature, precipitation, wind, pressure, pressure over the oceans, over land surfaces, solar radiation and its intensity, humidity, the water vapor content in the air, sea surface temperatures, greenhouse gases, and I'll talk a little bit more about those in a second. For the climate assessment itself, we really focused on, in terms of a change in some of these variables, we focused on temperature and precipitation. Okay, so we can move beyond just a definition of climate and ask the question, well, what is climate change? When we talk about climate change, it's really just a long-term shift in the statistics of the weather that we've observed historically. As a quick example, it could show up as a change in climate, say temperature or precipitation for a given place and time of the year, and it would change from one decade to the next or over multiple decades. Because so many systems are tied to climate, a change in climate can affect all of the aspects or many related aspects of where and how people and plants and animals live. This includes things such as, especially in Montana, food production, the availability and use of water, and just generally associated health risks, things like smoggy or days of fire when smoke becomes nested in mountain valleys across western Montana. As another example, a change in the usual timing of rains or temperatures can affect when plants bloom and set fruit, when insects hatch, or when streams become their fullest. So let's take a step back and ask what causes climate change. When we talk about climate today or into the future, we really need to remember that climate of the Earth has always changed and it will continue to change. Historically, the Earth's climate has changed naturally over periods of hundreds of years to millennia. A lot of this is well documented. Natural factors that have contributed to climate change include differences, orbital cycle around the sun, the intensity of solar radiation, ocean circulation patterns, the extent of ice and snow cover, and additionally, every now and again, volcanic eruptions, which contribute significant quantities of ash to our atmosphere. All of these processes and their occurrence have been well documented in the past, and they're linked to natural climatic change. They're also, I should point out, they're well observed and incorporated into future climate change analyses and modeling efforts today. One of the major points is that since the Industrial Revolution, our climate has changed at a rate faster than has ever been observed in the known history of the Earth. So it's well documented and studied that this rapid rate of change has been caused by changes in our atmospheric chemistry. Specifically, we call these greenhouse gases. Greenhouse gases in the atmosphere, at certain levels, this is a good thing. They trap outgoing heat energy from the Earth's surface, and this leads to an increase in temperature. We experience changes in temperature with the daily sunrise and sunfall. That change in temperature is associated with trapped heat energy in our Earth's atmosphere, and we see an increase in temp seasonally as well. However, in the last century, we've been releasing greenhouse gases to the atmosphere really at an increasing rate. The primary contribution of those gases is the burning of fossil fuels, such as oil and coal. The graph that I've shown here on the right is kind of a quintessential slide. It shows the increase in CO2 concentrations, one of the major greenhouse gases, over the last 50 years. I checked this morning actually at around 6 a.m. prepping for this talk. And as of this morning, current CO2 concentrations are at about 404 parts per million. So this graph goes up to 2010. This is a level that hasn't been reached in more than 650,000 years. So at the same time, as we've seen increases in CO2 and our greenhouse gases, we're also seeing an increased warming of our atmosphere, our oceans, our land surfaces, and that's been occurring steadily over the last 100 years. Okay, so change in temperature due to increased trapping of heat in our atmosphere, that's just one aspect of climate change. Here's just a general diagram of the hydrologic cycle. I've showed that on the right-hand side here. I show this at the beginning of my watershed hydrology class that I teach every semester. And fundamentally, if we simplify this, the sun and its energy are the engine for the hydrologic cycle. The sun's energy is utilized in the process of evaporation. Essentially, that heat energy causes the vaporization of water from surface water bodies, from wetted soils, from wetted leaf surfaces, as well as contributes to transpiration from plants. All of this evaporated and transpired water is conveyed as water vapor over our oceans, our land surfaces, and that's due to convection, just differences in atmospheric temperature that cause winds and transport of that water vapor. Eventually, though, this water returns to the ground as precipitation, and this cycle happens continuously. We call it the hydrologic cycle. Okay. One of the key points here, though, is that as we trap more heat energy due to greenhouse gas increases, we're seeing increased rapidity in the hydrologic cycle. So warming temperatures are contributing to greater evapotranspiration, generally decreased soil moisture, greater water vapor in our atmosphere due to increased evaporation, and subsequently, we can expect greater and more intense precipitation events. So precipitation is changing as well. Collectively, these changes in temperature and precipitation are causing wide-ranging impacts across the globe. Some of these include melting snow and ice, glaciers, which are then contributing to rising sea levels. We're seeing more extreme heat events, fires and drought, one relevant thing here in Montana, as well as just more extreme storms and floods. What I'll point out, though, is that these impacts vary across the globe, really due to the complex nature of the global climate system, as well as the connectedness of the hydrologic cycle. These things change at varying rates depending upon where we are in the Earth. So my point here is that some of these issues are really relevant to Montana and others aren't. Ultimately, one of the goals of the climate assessment is to provide a local look at changes in Montana, and then really provide or discuss their potential impacts for people here in Montana. Stepping back from that, my goal in the seminar today is to provide a picture of how and where Montana's climate has changed, and then simply discuss how it will progress this century, showing some results from our global climate modeling exercise. This talk is really meant to set the stage for upcoming webinars that will be issued from the remainder of the climate assessment team. All right. So let's begin by taking a look at the current state of our climate. Here's an updated map of Montana's mean annual temperatures. When I say mean annual temperatures, these were done as an analysis for the last 30 years, from 1950 to 2015, and it's based on an analysis done for the period from 1980 to 2010. This is what we'd consider a climate normal, or a moving window of 30 years. So generally looking at this figure here, and as we all know, Montana is very topographically complex. We have a very mountainous region, the Rockies in the western part of the state. And this causes some pretty big differences in our temperature across the region. Generally, the average annual temperature for the state is about 45 degrees Fahrenheit, and again, that's based on an analysis of the most recent 30 years. Differences in temperature are really dependent upon local elevation and the distance from the continental divide. Western Montana's annual average temperatures are generally cooler at roughly at around 39 degrees Fahrenheit. And eastern and central portions of the state, the flatter portions of the state, tend to be a little bit warmer at about 44 degrees Celsius or 44 degrees Fahrenheit. Excuse me, I'm getting my units mixed up. Okay, so let's kind of take a step back and move from our current climate to really where we've come from. So taking a look back from 1950 to present, annual average temperatures are increasing for the entire state. I've shown the rates of change or increase in temperature per decade for the 7 climate divisions across the state. Generally, and if we were to average this across the different regions within the state, the increases have been about 0.42 or almost a half a degree Fahrenheit per decade. And this is similar to rates of temperature increase across all of the climate divisions that encompass or compose the state. Also, I haven't shown it here, but in a similar way, annual maximum and minimum temperatures have also increased across the different regions, and that ranges from about 0.6 to 0.3 degrees Fahrenheit per decade. So if we look at this in a cumulative sense, since 1950, the state average annual temperature, it's increased by about 2.7 degrees Fahrenheit. Just for a broader context or for comparison purposes, this is little under double the rate of increase when compared to our national average. So for the United States on average or as a whole. Okay, so moving on to take a kind of a current look at precipitation. Again, the amounts and form of precipitation falling as rain or versus snow, that varies widely across the state. The majority of our wintertime precipitation, and we all know it right now looking out the window, the majority of that precipitation in Montana falls as snow. And this snowpack is a really important resource. It accumulates in the mountains, and it's really our most significant source of water to valley bottoms throughout the summer and later into the growing season. So this is also strongly influenced by elevation and proximity to the continental divide. If we look at our map here, I've shown the distribution of average precipitation, again for that 30-year period. Our current average annual precipitation across the state is about 18.7 inches, so across the state as a whole. Western Montana, again, receives about twice as much precipitation annually as eastern Montana. So between 22 to 30 inches falls in western Montana. That tends to be higher at higher elevations where snowpack accumulates, and lower down in the nested valleys. In eastern Montana, between 12 to 14 inches falls, and between 12 to 14 inches falls in eastern Montana. Thinking about the seasonal distribution, precip in western Montana is also much more even due to the flow of moisture-rich air from the Pacific coast. For eastern and central Montana, between 65 to 75% of the annual precipitation occurs in the late spring and into the summer months. So if we were to take a look back and move back through the precipitation record, so going back to about 1950, there has been no change in annual precipitation over the past 65 years, and that's for the state as a whole. In the previous slide, I discussed the changes in annual statewide average annual precipitation, and really we haven't seen any for the state as a whole. In this slide, I've shown that we do have changes. They're just more localized and they vary by seasons. So here I've shown precipitation changes in precipitation amounts on the left-hand side for spring precipitation, and on the right-hand side, changes in winter precipitation. So for the left-hand slide, in eastern Montana, spring precipitation is increased actually by 0.2 to 0.3 inches per decade. No changes in summer and fall precipitation were detected across any climate division or any region within the state. As I mentioned, if you did hear me, it was actually kind of nice to see that increase in eastern Montana. Just talking to a lot of farmers out in Sydney and other locations, they have indicated wetter conditions in the spring in the last couple of decades. They've indicated that they've been seeing that. Seasonally, though, the largest changes in precipitation have been in the wintertime, and this is again a combination of precipitation as rain and snow. And we've seen significant decreases in western Montana and parts of central Montana. Um, so those decreases have occurred at a rate of about almost over half an inch, so about 0.57 inches in the northwestern part of the state, up and down to about a tenth of an inch in central and north central portions of the state. Um, One thing I should point out, this change has been pretty well documented in other Western states, and really evidence suggests that the influence of natural climatic variability is occurring here. It's associated with more frequent occurrences of the El Nino Southern Oscillation, and I won't go into too much detail on that, but it's associated with warmer sea surface temperatures off the Pacific coast that cause a shift in our jet stream, and typically in Montana. When that happens, we see warmer and drier wintertime periods. It's also coincidental with the Pacific Decadal Oscillation, which is another large kind of atmospheric connection between the oceans and ocean temperatures. Okay, so just to take a step back and take a breath, let's take a look back at where we've been. In general, for our historical climate, on average, temperature has increased by about 0.42 degrees Fahrenheit per decade over the last 65 years. If we sum that up, it's an overall increase of about 2.7 degrees Fahrenheit. And again, this is a slightly faster rate of warming relative to the national average. Statewide, the amount of average annual precipitation has shown no statistically significant trend over the past 65 years. Okay, so let's now move forward. We've talked about the historical climate, kind of our current climate conditions, but probably more what people think about when they signed on for this lecture. Moving forward in time, we use global climate models, and we use these to determine potential changes in Montana's future climate. I'm just going to give a brief description of global circulation and global climate models. Generally, they're considered very important tools for improving our understanding and predictability of climate behavior, both on seasonal. So the National Weather Service uses these for extended or seasonal forecasts, but as well annual, decadal, and even centennial timescales. So we use the models to investigate the degree to which observed climate change or climate changes are due to both natural variability, human activity, but more importantly, a combination of both. The results from the projections provide a essential piece of information to inform our decisions at regional and local levels. Some examples of kind of how they're used in the decision-making process include water resource management. A lot of times the results from these will be fed into a hydrologic model and used for kind of assessments of surface water flow and changes in surface water flow, as well as groundwater. They're used in agriculture, so assessing kind of how agriculture may change moving forward and how we optimize for those changes, as well as just transportation and planning in general. So to kind of talk a little bit more about the details of a climate model, it's a complex mathematical representation of the Earth's major climate system components and their interactions amongst one another. So if I was to kind of bracket those, the major components would include the atmosphere, our land surfaces, all of our oceans and surface water bodies, as well as sea ice in upper and lower latitudes. Generally, I've showed a kind of a schematic of a general climate model on the right-hand side here. Climate models divide the globe into a series of grid cells, and each of these represents a specific location or geographic location, as well as the elevations of those locations. Each of these individual grid cells has an equation, and it's calculated across this global grid for climate variables like temperature, precipitation, and the longer list that I showed you earlier. In addition, the different parts of the model are able to exchange, so they're coupled. Each grid cell is linked to the adjacent grid cells, and they're coupled and they're able to exchange heat, water, and momentum or energy between one another. So they interact with one another as a kind of a coupled system. They can capture the hydrologic and atmospheric cycle and movement of heat and moisture over the globe. Okay. One of the key limitations when we think about a local assessment of a global climate model, one of the limitations is that they have very coarse resolution. So for most impact studies, such as this one, or if we were assessing changes in precipitation and temperature, or say risks of drought, we really require that information at a much more detailed or local scale. In this case, what we do is embed a regional climate model. And really, a regional climate model is just a higher resolution atmospheric or circulation model. In this approach, the larger global climate model determines, really, we use it to determine large scale effects of changing greenhouse gas concentrations or volcanic eruptions or all of the other variables on global climate. The climate calculated then by that global climate model or those larger grid cells is used as an input by the regional climate model. Generally, regional climate models do a better job of resolving the local or small scale information about topography in a given landscape. That's very important here in Montana, as well as our land cover and many, many other factors. But this allows us to provide weather and climate information at resolutions less than 5 kilometers across Montana. So for our specific climate analysis, I'm going to talk about more of the details behind the analysis that we performed. For our specific climate analysis, we used a combination of global climate models called CMIP-5 models, or the Coupled Model Intercomparison Project. And we link them all together or combine them all in what we call an ensemble. So we use 20 models. And these models are the ones that have been accepted by the International Panel on Climate Change. Generally, they work well in our region. By using many models in an ensemble, we're able to determine really a measure of certainty in the direction of trends of the models, whether the trend is positive or negative for any given climate variable, as well as their magnitudes. In my analysis today, I'll talk about the percent agreement between the 20 models in our ensemble. This is a general measure, or it represents a measure of uncertainty for the ensemble. So represents the number of models that project the same sign of change. In other words, is the change positive or negative? So as an example, if the median value for temperature change in a given region by the 20 models is positive, and 18 out of 20 of those models project that positive change, the percent agreement would be fairly high. It would be around 90%. Okay. For our downscaling approach, we used a more simple approach. We used a statistical downscaling method. And this is a big word, but it's called the multivariate adaptive constructive analogs approach. So MACA for short. In English, this approach uses historical observations at high resolution, and it develops a relationship with those historical observations and historical modeled global climate model variables. This statistical relationship then gets used to project future conditions and to downscale the global climate model to higher resolutions. Okay, it's important to note that there are many different kind of forcings that we consider in these models. When we talk about forcings, these are called representative concentration pathways. Really, it's a projection of future greenhouse gas concentration and scenarios for those. So generally, the higher the value, the higher the amount of heat that's going to be trapped in our atmosphere from increasing greenhouse gas emissions. So as an example, and for our analysis, we used the concentration pathway scenarios 4.5 and 8.5. The representative concentration pathway 4.5, it's considered really a stabilization scenario. So it's where we're able to reduce greenhouse gas emissions by middle of this century. The RCP 8.5 is a scenario kind of business as usual. It's a scenario where greenhouse gas emissions increase throughout the 21st century. And for this scenario, it's assumed that society makes little progress in curbing greenhouse gas emissions. So I'll talk about the results from this analysis. We evaluated the 20 downscale models at 2 future time periods. We did the mid-century, so from 2040 to 2069, and the end of the century, so 2070 to 2099. 30-year averages of these projections are compared to historical 30-year average, and that results in a projected difference or change from historical conditions. So again, highlighting, we did, in the results that I'll talk about today, we looked at both of the concentration pathways or emission scenarios. For my talk today, I'm going to focus on the mid-century projections. Okay, so right in and take a look at the results. I've shown them in a map form here across the different regions of Montana, and for the 2 greenhouse gas emission scenarios. The lower emission scenario is on the left, and the higher scenario is on the right. So again, 4.5 and 8.5. If we look across these maps, generally average annual daily temperatures are expected to increase by mid-century in both scenarios. In the lower emission scenario, most of the state is projected to have increases around 4.5 degrees Fahrenheit. The higher scenario projects larger increases in temperature of around 6 degrees Fahrenheit by the end of by the middle of the century. So while there are some small differences between all of the climate divisions, generally what you see is one big color blob. So it suggests in magnitude these changes are consistent across the state. And I should highlight that there's a large model agreement between these 2 scenarios, so 100% model agreement in terms of the direction of change. To put these changes in context, remember that our historical change since 1950 to present has been about 2.7 degrees, so a little less than half in terms of what we're looking at in terms of future conditions. Okay, again, there was a 100% model agreement for this. Okay, it's also nice to know how temperatures are going to be distributed seasonally across the state. The figures I've shown here show the monthly change in temperatures for mid-century across the 2 emission scenarios. So low emissions on the top and higher emission scenario on the bottom. Generally, average monthly temperatures are expected to increase across, again, all climate divisions and both scenarios. What really stands out here is that summer and winter generally have larger projected increases relative to the spring and fall. This is an important consideration because it may indicate the potential in the wintertime for earlier losses of snowpack associated with warmer temperatures, as well as increased rates of evapotranspiration and therefore dryness in the summertime. In the highest scenarios, so RCP 8.5, one other thing that stands out, August has the largest projected change across all climate divisions, so upwards of 7.5 degrees Fahrenheit. Okay, moving on and really starting to think beyond just measures of temperature, but extreme days. Extreme heat days are really important here in the summertime. It impacts our crops in terms of overheating, as well as just our health in general. So thinking about extreme heat days, we also calculated the number of annual days at mid-century where maximum temperatures exceeded 90 degrees Fahrenheit. Again, the 2 scenarios are shown, the lower emission scenario on the left-hand side, the higher emission scenario on the right-hand side. Generally, the increase across all climate divisions in both, there are large differences in both the magnitude and change among the different climate divisions for each scenario. So in the low emission scenario on the left, the northwest and north central parts of the state are expected to have increases of around 5 days per year in terms of those extremely warm days. Eastern and southern parts of the state are expected to see increases of around 25 days per year. And again, this is probably going to occur around the summertime, 25 more days per year in eastern parts of the state. Similar spatial patterns exist for the high scenario, but the magnitudes of those changes increase. So in the northwest and north central parts of the state, increases around 11 days per year are expected. In the southern and eastern parts of the state, increases are projected to be around 33 days per year. Again, in this case, as with the annual temperature, there's a 100% model agreement. So relatively high certainty in that change. Okay. Moving on, another important consideration is the number of freeze days, or alternatively, you could consider this an increase in the growing season. So the number of days where minimum temperatures are above 32 degrees are projected to increase across all climate divisions and for both emission scenarios. Again, you can think of this as a freeze-free season or an extension of the growing season. In the low emission scenario on the left, freeze days increase by about 30 days per year in the western part of the state and around 23 days per year in the eastern part of the state. So kind of the opposite trend that we saw days above 90 degrees Fahrenheit. Moving to the higher scenario, freeze days are expected to increase by about 41 days per year in the western part of the state and around 32 days per year in the eastern parts of the state. Again, one of the implications of this increase is in warmer days during the shoulder seasons. It probably means that we have a longer growing season length in terms of the definition of a growing season based on temperature. And this could benefit our agricultural productivity across the state. But one thing I'd like to point out is keep in mind plants can't grow without water in unirrigated settings. So let's take a look at the other side of the equation. This is precipitation. So here's a look at our annual precipitation and projected changes. Precipitation is actually projected to increase by mid-century across the state and in both scenarios. There's moderate to high agreement across the 20 different models. In the low emission scenario, increases of around 1.3 inches per year are expected in the northwestern parts of the state. In the southern and eastern parts of the state, increases are around 1/10 of an inch per year. In the higher scenario, average annual precipitation is projected to increase by around 1.6 or 1.5 inches per year in the northwestern portions of the state and around 1.2 inches per year in the southern and eastern portions of the state. So generally on an annual timescale, this does suggest that it is going to become wetter. And again, there's moderately high model agreement. Okay. While annual, what I should mention is while annual increases in precipitation are expected across the board, the monthly and seasonal projections in terms of monthly distributions and seasonal distributions of precipitation are a little more diverse, and there's less overall agreement. Winter, spring, and fall are projected to have increases in precipitation for both scenarios. The low scenario again on the top and the higher scenario, emission scenario on the bottom here. And in both scenarios, spring is expected to have the largest increases. In the lower scenario, spring months are expected to increase by about 0.2 inches per month. In the higher scenario, spring months are expected to increase by about 0.4 inches per month. In contrast, though, what you see in the center of each of these plots, summer months are expected to have decreasing precipitation in both scenarios. One thing I'll point out here, though, is it's model agreement in terms of the direction of that trend. It's really low or fairly low. So in both scenarios, summer precipitation is expected to increase by about 1/10 of an inch per month. But the model agreement was about 65%. So if we were at 50%, it would mean that none of the models agree. So pretty low agreement on that one. Okay. We also kind of developed two of our own metrics in this analysis, and we did this to evaluate changes in really the frequency of wet and dry events. For changes in the frequency of dry events, we use the maximum number of consecutive dry days per year. This can be thought of an indicator of potential drought conditions. Here we define dry days as those days in which precipitation is less than 0.01 inches, and we essentially calculate the maximum number of consecutive days that meet this limit for each year, and then average that value over the 30-year time period. Generally, we find that there's a modest increase in consecutive dry days, so about 0.5 or actually less than 0.5 days per year. And again, I'll point out in this case, though, there's very low model agreement in terms of the direction of that trend. So it's about 60%. Okay, moving on to number of consecutive wet days. In this case, we evaluated changes in wetter conditions, so high intensity and consecutive wet days. We calculated the number of days per year where precipitation is greater than 1 inch. So that's a lot of water. This can be an indicator of intense rainfall periods and potentials for flooding. For this metric, we again find very small changes. So again, less than about 0.5 days in high intensity precipitation events and across both emission scenarios. In this case, though, there is high model agreement, so fairly high, suggesting that these changes will occur. Okay, so to summarize the projection sections in a nutshell, temperature is increasing across the state. It has been increasing historically. And when we look at the projections themselves, the amount of increase is fairly sensitive to emissions. So with increased emissions, we see pretty significant changes in projected temperatures moving into the middle of the century. One thing I didn't highlight is that the end of century projections are all in agreement as well in terms of that temperature trend. The magnitude increases in terms of the amount of change. Generally with temperature, there's really strong model agreement. So suggests that there's really low uncertainty in those estimates. Things are going to get warmer. There are spatial differences in the extremes that we see across the state. So things like days above 90 degrees Fahrenheit, we'll see a higher frequency of those days in eastern portions of the state relative to the western portions. Really, that's buffered by the Pacific coast and cooler air moving from the Pacific coast that intersects the Rocky Mountain Divide on the western portion of the state. Precipitation's increasing across the state. In this case, precipitation and the change in precipitation was a little bit less sensitive to those emission scenarios, the high versus low emissions. Generally, there was moderate model agreement, a little bit higher uncertainty, especially in terms of the seasonal differences in precipitation or month-to-month variability. And again, we did see spatial differences in extremes or in terms of very intense rainfall events in consecutive days, so days greater than 1 inch of rainfall. There were spatial differences, but the number of days was relatively low, so about half a day per year increase. Okay, so to wrap it all up, and in a nutshell, temperature has increased historically in Montana. And if I were to put it simply, precipitation has stayed about the same historically. One thing to point out here, so to caveat that statement, Wyatt Cross will be discussing trends in snowpack historically. In terms of the depth of precipitation or the amount that we receive, for the state as a whole, that hasn't changed much, but the timing of that precipitation has changed. In terms of snowpack, again, with those warmer temperatures, we're seeing earlier loss of snowpack, and again, that's a critical resource in terms of stored water and our water towers, which are the mountains that subsidizes valley bottom systems. So with increased temperatures, historically, we have seen earlier snowpack and snow melt. Mid-century conditions in terms of the projections, they're going to be hotter and possibly wetter, except for the summertime. So we saw some indication of drier conditions during the summertime, but again, the model agreement was low in that case. So one thing I'll point out, I gave you guys a lot of information today, and I really focused on the kind of projections or the analysis for historical climate trends in terms of temperature and precip and our projections moving forward. I didn't spend a lot of time on kind of the potential impacts and the changes that we're seeing relative to agriculture, our water resources, and forests. I want to save the best for last, and that's what's coming with the upcoming webinar. So I'd really encourage everyone to tune in. Future presenters will talk about these changes relative to these different sectors. And with that, I'd be happy to take some questions or have a discussion.
Great. I'm just going to jump in here real quickly. Thanks so much for the presentation, Kelsey. That was awesome. I know some people do have to leave at noon, so I wanted to let you know that Kelsey will take some questions, and I see there are several in the question box there. We will also archive these questions and answers, and we will put them on the webinar archive page. So if you have to sign off and we haven't had a chance to answer your question, you can look for that link. It's actually in the upper right-hand corner. There's a link that says Webinar Archives. That's where we'll be posting the recording of this talk, as well as any associated documents and any questions and answers. So Kelsey, maybe, I don't know if you can see the question pod there. Maybe we'll just start at the bottom. Someone said the temperature and precipitation data is really good work. Have you or others done similar work that is historic versus projected with other climate variables like cloudiness, wind, relative humidity, etc.?
Yeah, great question, Jane. That information all exists, and this same approach that we've applied has been or can be summarized and compiled for those other variables. Yeah, you're spot on there. Cloudiness, wind, relative humidity, those are all really important when we think about aridity of the environment and potential impacts in agriculture. For this assessment, we had a short amount of time and a lot of work to do to get it up and running. And so, my simple answer is that's in the cards moving forward. This is not a one-off, and I think Kathy and the rest of the group have some really concrete plans for continuing this, expanding into other sectors, but also getting into much more detail in terms of the other variables of climate that I haven't discussed today.
Great. And then it looks like there's a question after that about nighttime temperatures. How have nighttime temperatures changed, historic versus printed in future? And this greatly impacts disease formation in crops. So it's an important consideration.
Absolutely, good question. I could have spent all day talking about some of the other additional analyses. So while we didn't do things like relative humidity, cloudiness, wind speed, we did take a look at changes in minimum temperatures and really nightly minimums and daily minimums and maximums. So those will all be included in this larger analysis. The short answer is yes. Minimum temperatures have changed. We're seeing an increase in average annual minimum temperatures. They're going up.
Okay, and then it looks like someone had asked if there are projections for changes in soil moisture over the seasons.
Yeah, that's another thing for the future. I think that's you, Marie. That's the holy grail in terms of Montana and what we really need to know. It's hard enough to do that currently and get good spatial estimates across the state. But one of the major drivers of our soil moisture, especially out in central to eastern Montana, is really evapotranspiration, seasonal patterns of rainfall, and how those two align. And so we haven't done that in this analysis. I think it's a fantastic point and something that could absolutely be done into the future.
Great. Before we answer the next question, I just wanted to mention if anybody has to jump off but does have a question, they can go ahead and type it, and we will do our best to answer those and post them on the website. Kelsey, I'm going to jump up. Somebody had asked about if you could explain further the concept of model agreement.
Brad. Yep. Thanks, Brad. Good question. I went through that really quickly. It's a fairly simple concept. So the idea of using a lot of models is that they all have slightly different configurations, or what we call structures. They incorporate different concepts related to the kind of the coupling and flow of winds, of moisture, of our oceans circulation patterns. And some do better at some aspects than others. And so the idea is that you put these together to kind of cover all of your bases. And so the reason you want to think about model agreement is that you're putting them together to get a representative measure. And we look at that model agreement. If all of the models are showing the same general trend and similar kind of range or change in a given variable, like temperature or precipitation, then we say the models have high agreement. 100% of the models are projecting the same change. Now, if half of the models say that temperature is going to decrease and the other half say that it's going to increase, that would be really poor model agreement. And so it's a way for just to kind of check the physics behind the modeled estimates and say, are we getting close to the right answer?
Cool. And Kelsey, before we wrap up, I wanted to jump up. Terry had posted a couple of comments. One is about the timing of precipitation, particularly in eastern Montana, and then another comment about day length and how that impacts the growing season. Those might be easier just for you to read there toward the top of the chat box.
Okay, let me scroll up 1 second. Yeah, so Terry, it looks like your comment was day length doesn't change with climate change. So a longer growing season does not directly correlate an increase in production. Absolutely. There are still some sideboards in terms of the length of the day, and we're going to run into that both. Well, we'll start with that in the spring. We're still going to wind up there in the fall. The idea is that the kind of within those shoulder seasons, we do expect increased temperatures and therefore more and more available energy in terms of growth. I think one of the other things that is really important to highlight is that our typical measure of a growing season is based on temperature alone. And it's always struck me that we also need to consider the water that the plants need, and that's a big issue here in Montana, where the vast majority of our agriculture is rain fed, and so the timing of that precipitation, along with that increase in energy, are going to be really, really important for us in terms of understanding what our actual growing season looks like.
Great. Well, Kelsey, I think we've hit all of our questions. We'll maybe just keep that chat board open just for another moment in case any people have some last comments or questions. Just one more time, I'll let everybody know we'll be here next Friday at 11 a.m. again. It's the same link that you used today. We welcome you to share the information about this class with any of your colleagues or friends or anybody who would be interested. You can certainly share the link to the archive page as well. We do ask that people register for the class. It is free, obviously, but we do just like to know kind of where people are coming from and what questions they have. So please direct them to that same site where you registered, and we'd love to have even more people next week. So Kelsey, thanks so much for joining us. That was a great presentation, and we really appreciate it.
Thank you, and thanks to everybody for hanging in there with me with the technical